Okay, dear all, thank you, everyone. My name is Ramon. I am a professor with National Institute of Telecommunications, Inatel, from Brazil. And the title of my presentation is Microwave Photonic Techniques for 5G, 6G fiber wireless systems. The goal is presenting some research activities we have carried out here in Brazil at Inatel. Talking about the environment in which the research had been realized. It has been realized in the lab WACA. It means wireless and optical convergent access. In this lab is coordinated by Professor Arismar and has two main research areas: antennas for radars and 5G networks, and optical wireless networks. Here, the part of the infrastructure of this lab in terms of equipment. Now we have more than 2 million euros of equipment and device in this environment. Okay, the agenda. I'm going to start with the motivation for the work. Next, I will quickly present the Brazilian 5G transceiver. It's a transceiver designed at Inatel. Next, I'm going to present analog RF solutions for 5G. It includes microwave photonic techniques. And finally, the conclusions. Motivation. The first motivation for the work is 5G. 5G, we know it have challenge scenarios. It includes enhanced mobile broadband, massive machine type communication, ultra reliable and low latency communication. There is also an highlighted use case for long range counterings and the longer range coverage to connect the unconnected or to provide connection in remote areas. And so they are challenge scenarios. In the 5G context, the 5G new radio standard has been recently launched by 3GPP. It includes two frequency ranges, frequency range 1, frequency range 2. The novelty is frequency range 2, that is occurs in millimeter waves, and there are some options for bandwidth. 5G brings also the 5G X-Hall vision. It includes backhaul, connection between central unit and the core network, mid-haul, a connection between central unit and a distribution unit, and front-haul, which can connect distribution unit to the remote radio unit or central unit directly to the remote radio unit. Front-haul can be optical and wireless, although it's mainly based on fiber optic. And the motivation of our work is design fiber optic front-haul solutions for 5G. Here is an example of application in which we have work. In this scenario, we can exploit a passive optical network from an internet service provider, for example, to implement the 5G front-haul over this network. So we can take a passive optical network and 5G signals being distributed over this work, providing remote picocells at millimeter waves, or remote macro cells or supercells for longer range coverage. So the main motivation for the work is design RF-based multiband front-haul for 5G fiber wireless systems. Let's go to the Inatel 5G transceiver. This transceiver has been designed by the Radio Communications Reference Center project at Inatel. And the main goal of this radio is enable long-range coverage. So we have realized some tests with up to 100 kilometers. The main features of this equipment its flexible waveform. This radio can operate with OFDM, generalized FDM, and FOFDM, which are new waveforms, candidate waveforms for 5G. This radio has also digital predistortion as a feature that improves, for example, error vector magnitude, EVM, and has been implemented in software-defined radio platform with LabVIEW communication. This radio is part of the 5G range project also, and more information can be found in such links. Let's go to the analog radio verifier solutions for 5G, 6G. Okay, the first solution is deploying multiband 5G Fronthaul using single drive Mach-Zehnder modulator or dual drive Mach-Zehnder modulator. In the first approach, we consider single drive Mach-Zehnder modulator. And our goal is to transmit two RF-driven signals, one at 26 gigahertz and another at 3.5 gigahertz. Frequency range 1, frequency range 2 of the 5G radio standard. So since STM single drive Mach-Zehnder has just one RF port, it's necessary to use a RF combiner to deliver these signals to the modulator. So we have used a RF combiner to perform this function, and the modulator receives also a optical wavelength from a laser. The electrical field in the optical domain has been launched in the single mode fiber and reached the photodetector. The resultant signal is analyzed in an electrospectral analyzer. So device, a variable optical attenuator and an optical power monitor, they have been used to control the power at the PD input. In a second moment, we use the same setup, but we replace the single drive Mach-Zehnder modulator by a dual drive Mach-Zehnder modulator. And the advantage is since the dual drive Mach-Zehnder modulator has two RF ports, there is no requirement to use an external RF combiner. It's the first advantage of using dual drive Mach-Zehnder modulator. Another advantage is the fact that the dual drive Mach-Zehnder modulator enables two independent bias voltage control, one for the 26 gigahertz RF driven signal and another for the 3.5 gigahertz RF driven signal. So it's the main difference between these setups. Let's go to the results. More information about the part of the information about the setups can be found in this publication in Opticommunications. Okay, let's go to the results. We have analyzed the SNR at the PD outputs as a function of the optical power at the PD input and as a function of the coexistence among the signals. So for the single drive Mach-Zehnder modulator. In the first moment, we have turned on only the 3.5 gigahertz signal and measured the SNR, which results in the black curve. Next, we make the 26 gigahertz RF driven signal on, and we can observe that there were no negative impact on the 3.65 gigahertz SNR. So the coexistence scenario is okay. In a second moment, we make only the 26 gigahertz on and result in the gray curve for SNR. Next, we turn on the 3.5 gigahertz and we observe 10 dB of SNR degradation when we make the 3.5 gigahertz on. 15 dB SNR degradation in the 26 gigahertz signal. And it can impact the coexistence of these signals. Okay, let's go to the analysis for the dual drive Mach-Zehnder modulator. For 3.5 gigahertz, there were no significant modifications. There were no degradation in the 3.5 gigahertz SNR as a function of the presence of the 26 gigahertz. The curves are proximal. In a second moment, we measured again the 26 gigahertz SNR, gray curve. And when we make the 3.5 gigahertz on, we observe a degradation of 1.6 dB, a degradation which is lower than that from single drive Mach-Zehnder modulator. So these results indicate the advantage of using dual drive Mach-Zehnder modulator for deploy multiband 5G Fronthaul. Okay, second technique, multi-application fiber wireless system using dual drive Mach-Zehnder modulator. The idea in this proposal is exploiting the passive optical network from an internet service provider to deploy the multiband 5G Fronthaul. So we have an optical network from an internet provider, here OLT, here ONU, and we have used this network to implement the 5G Fronthaul. It has been implemented using 3.5 gigahertz and this frequency and the 26 gigahertz. Here using the 5G transceiver from Brazil. So we transmit these three frequencies simultaneously, joining with the GPON signal, and implement a cell at 26 gigahertz, a cell at 3.5 gigahertz, and a cell at this lower frequency for long range. In parallel, we have the wired fixed access for internet. And it works well. Here some photographs of this implementation. Here the indoor environment with the optical setup. And here the outdoor environment. The antenna, the line of sight. Here the 5G transceiver from Inatel. More details can be found in such publication and Journal of Lightwave Technology with this title. Some of the part of the results. This here on electron spectrum for the 3 RF-driven signals transmitted simultaneously. So one can observe the lower frequency for long range. One can observe the 3.5 gigahertz signal, and here the 26 gigahertz signal. For long reach, we have obtained a constellation with 16 kAm, FOFDM, and the throughput of 20 megabits per second. At 3.5 gigahertz, we have transmitted the 5G radio standard. And we have achieved more than 200 megabits per second with throughput. And EVM, error vector magnitude, has been met the 3GPP requirement for the 5G radio standard. The same occurs for the 5G radio at 26 gigahertz. We achieved 2 gigabits per second, and the EVM has been met the 3GPP requirements for the 5G radio standard. The third technique, this one is called photonics assisted amplification, PAA. The goal here is using the optical link not only for data transmission, but also as a mechanism to provide RF gain after photodetection. So we can improve the power at the photodetector using electron amplifiers. But electron amplifiers in millimeter waves can be costly, can be challenging. So we designed a technique to improve that power using the optical link. In the first stage is a radio over fiber link conventional, but with the dual drive Mach-Zehnder modulator to combine different RF signals. The PAA consists in including an stage in such link. This stage is used to stimulate the far-wave mixing nonlinear effect. And stimulating far-wave mixing, we can observe the optical spectrum present side bands more intensely in comparison with that from a conventional radio over fiber signal. And the photodetection of such field results in RF gain after photodetection, about 15 dB of RF gain. To stimulate far-wave mixing, we have used an EDFA to increase power, and have used an high nonlinear fiber. The parameters of such fiber is presented here. Okay, let's go to the results. Here's some photographs of implementation. And this technique provides gain for baseband and RF signals. Both. In the first case, gain in an RF signal at 28 gigahertz, one can observe about 15 dB of RF gain. The curve in the spectrum in red is a conventional radio over fiber link, and the spectrum in black refers to the PAA, the conventional RF link assisted with PAA. And here, the gain in a baseband signal. It occurs also for a band signal. So this technique can be employed to amplify baseband or RF signals. It can be employed, for example, for backhaul or fronthaul, depending on the operator demand. Details of such results can be found also in such publication, optical fiber technology, with such title. The conclusions, and I will perform the vision and not a conclusion. The vision is deploying 5G toward 6G. The studies on 6G have already initiated. How are the techniques expected? Free space optical, visible light communication, terahertz communication, artificial intelligence, unlicensed spectrum, Internet of Things. This is solutions proposed for 6G that are already in studio. Here in Brazil, we have the Brazil 6G project, an initiative to start the 6G development in Brazil. It is happening at Inatel. Okay, thank you very much. I'm able for questions.